In this section, we need to go over properties of sine and cosine, the fundamental trigonometric functions, trig functions. I assume that you know about trig on triangles to some extent. We need trigonometry in terms of unit circles. We need radians, which is a different measure of angles other than degrees. We also need to look at kind of periodic functions and understand why sine and cosine are such, on circles, are such fundamental objects. So I do assume that you're familiar with trigonometry on right triangles. It typically people see things like, here's a right triangle, here's an angle theta, here's the opposite side, the side opposite the angle you're talking about, the adjacent side, the side adjacent to the angle you're talking about, and the hypotenuse, which I've marked as having, I'm going to use these actually for the lengths. The adjacent side has length ADJ, and the opposite side has length OPP, and this has length R. So that, yeah, you should have seen, for instance, that the sine of theta is the opposite side over the hypotenuse. So really, I mean, the lengths of those things. And the cosine of theta is the adjacent side over the hypotenuse. All right, but triangles aren't good enough for us for a lot of reasons. And there are a lot of things in the real world, a lot of functions, a lot of physical quantities that repeat, that oscillate, that kind of bounce back and forth between two values. Functions with properties like that are called periodic functions. So let me go ahead and define periodic functions. So a function, so this is a definition. A function f is periodic. We just want to say if it kind of repeats every so often, where the so often is a fixed value. So a function f is periodic if there exists some number, p, greater than 0, such that for all x in the domain of f, well, for f to repeat, it in particular has to be defined. So I want to say that for all x in the domain of f, both x minus p and x plus p are in the domain of f. And the values of f are equal there. So that f of x equals f of x plus p equals f of x minus p. So that the value of f just keeps repeating every time x goes up or down by p. This is what it means to be a periodic function. If there's a smallest such p, and there doesn't have to be a smallest one, for instance, a constant function would have this property no matter what positive p you pick, but if there's a smallest such p, so greater than 0, but a smallest one, that makes the function repeat. If there is a smallest such p, that p is called the period of f. And lots of physical processes yield periodic functions. And so we want kind of fundamental periodic functions. And it turns out that sine and cosine are fundamental periodic functions if you define sine and cosine not just in terms of triangles, but in terms of circles. You may have seen this before, and this will just be review. I'm not going to derive all the properties of sine and cosine that follow from this. I'm going to state a bunch that we need, and you can either take them as true or recall them if you've seen them already. So we look at a circle of radius 1 centered at the origin. We usually refer to this as the unit circle, circle of radius 1 centered at the origin. And I'm going to draw a bigger circle around it that I won't use much, but I just want, this is supposed to be a circle. That's not too bad. Suppose I take a general circle of radius r. So this smaller circle has radius 1. I'm drawing a bigger circle of arbitrary radius r. And then I want to look at the length of this arc, both on the unit circle and on this bigger circle of radius r. So let me call this length t and this length s. So this arc has length t, this arc has length s. I'm drawing arrows as though it's pointed because what we're thinking of doing is kind of marking, kind of a coordinate axis, but a circular coordinate axis that starts here at the point that would be 1, 0. Right, this would be the point. X is 1, y is 0, so 1, 0. I'm thinking of this as a starting point, and that the positive direction on this circular axis is counterclockwise measured from this starting point, or counterclockwise measured from here. So the reason I've got those arrows going is I'm indicating we're going in that direction, so in the positive direction. So consider this arc length t, this arc length s. Well, it's essentially similar triangles or similar sectors, similar arcs, kind of think similar curved triangles. The ratio of 1 to t is the same as the ratio of r to s, or let me say t to 1 is the same as s to r. So what you get is that length t divided by the length of the radius, which is 1 there, is the length s divided by the length r. Well, that means that these two circles have that, well, it means that t divided by 1 is s divided by r, which means that kind of this arc that has the same angle that you're used to, the angle didn't change, it has the same angle, gives us the same number. So this number is a measurement of this angle, right? Because it doesn't matter how big the circle is. If you just extend this line, so keep the same angle, you get the same number. That means we can use this as the measure of an angle, and this is called the radian measure of this angle. So, or we just say the angle is that many radians. So this is the radian measure of this angle, theta. But in fact, since it's just t, there's no reason to give it another name. It'll just turn out to be t, so maybe I won't call it theta. T, this is the radian measure of the angle. What angle? The angle that this ray makes with the positive x-axis. And a positive number means you've measured counterclockwise from this starting point. A negative number would mean you'd measured clockwise. So for instance, this would be that would indicate a negative angle. All right, that's the radian measure of an angle. So you think of, you're considering a circle as some kind of axis, and your origin is the point 1, 0, and counterclockwise is the positive direction, clockwise is the negative direction. Of course, once you get big enough, you'll come back around, so it's kind of a strange axis. Things repeat, but that's okay. We can live with that. What does this have to do with trig on triangles? What are sine and cosine? Well, let me draw a picture without all this stuff in it so I can just make it more clear what sine and cosine are going to be. So now let's just look at the unit circle, because we know that it doesn't matter what circle we take. If we took a bigger circle, we'd have to divide things by the radius, but there's no point in doing that. So take the unit circle, circle of radius 1, centered at the origin. Well, if you think of this as the angle, and really you could also mark the angle out here as just this length, or with a plus or minus sign, so here's some t. Then if you think of this as the measure of this angle that you're used to, well, if you drop a perpendicular right here, the sine of this angle would be the opposite side over the hypotenuse. But the hypotenuse is just 1, so the sine would be the opposite side, which would be the y-coordinate of this point. The cosine of this angle would be the adjacent side over the hypotenuse. But that's just the adjacent side, which is the x-coordinate of this point. So this point, if t is the angle, which is also the length, the arc length on the unit circle, you get cosine of t, sine of t, or the coordinates of this point. And in general, this is how we define sine and cosine for arbitrary angles, which could be bigger than going all the way around the circle, so bigger than 360 degrees. And I'll write how you convert between radians and degrees in a minute. But yes, this is what you do. What are sine and cosine? You measure angles starting at the point 1, 0. Positive angles, you go counterclockwise around the circle, that length, that distance. If you've got a negative angle, you go clockwise, the absolute value of that. Yes, you might come back around. That's why sine and cosine will be periodic. And cosine of t, by definition, is the x-coordinate of the resulting point. And sine of t, by definition, is the y-coordinate of the resulting point. All right, so that we can look at some examples. And they'll seem more friendly. Let me convert between radians and degrees. What you can see pretty quickly, or you should see, is going all the way around the circle. Well, that's the circumference of a circle. The circumference of a circle of radius 1, 2 pi times the radius, is 2 pi. So the total number of radians in going all the way around the circle, 2 pi radians, the abbreviation for radians, RAD. Well, how many degrees are in the whole circle? 360. So this is how you convert between radians and degrees. 2 pi radians equals 360 degrees. So you can divide both sides by 2. Pi radians is 180 degrees. Pi over 2 radians is 90 degrees. If you want a 45 degree, pi over 4. And then I guess the other two common ones would be pi over 6, which would be radians, which would be 30 degrees, and pi over 3 radians, which would be 60 degrees. Okay, so with that understanding, calculus is always done in radians. There are reasons for that, and we'll see them soon. It's that certain limits only come out to be so nice in terms of radians, which means the derivative formulas are only correct in terms of radians. So you always do calculus in terms of radians. So throughout the remainder of the book, whenever I mention an angle, if I don't explicitly say it's degrees, if I just say an angle of this without any units, I mean radians, because you just shouldn't mean anything else. in a calc class. All right, so let's look at some examples quickly, like what's the cosine of pi over 2? What's the sine of negative 3 pi over 2? Of course, I mean radians. Well, pi over 2, you should think 90 degrees if you need to. Pi over 2 radians, 90 degrees. Measured counterclockwise from here. Well, that would put you right up here. On the unit circle, the coordinates of that point, its x-coordinate is 0, its y-coordinate is 1. So this means the x-coordinate's cosine. So the cosine of pi over 2 is 0. The sine of pi over 2 is 1. What's the sine of negative 3 pi over 2? All right, it's negative, so you measure counterclockwise starting from here, and then you go 3 pi over 2. Well, pi over 2 is 90, another pi over 2, and then another pi over 2. Oh, you're at the same point. We came back to the same point. So the sine of minus 3 pi over 2 is the same as the sine of pi over 2. It's 1. And the cosine of minus 3 pi over 2 is 0. Well, yeah, every time you go all the way around the circle, so every time you go around another 2 pi radians, or whichever way, you can go around another 2 pi counterclockwise, or subtract 2 pi and go counterclockwise, you're going to end up at the same point. You call it a different angle because it's kind of, which way did you go and how far did you go, but you end up at the same point, so you have the same sine and cosine. Well, this is why sine and cosine turn out to be periodic. They are 2 pi periodic. They repeat every 2 pi. So sine and cosine, yeah, this is the abbreviation for sine. This is the abbreviation for cosine. When you write them out, the actual words are sine and cosine, but you don't see this too much. Sine and cosine are periodic with period 2 pi. Radians, but sine and cosine are 2 pi periodic. Every time you go all the way around the circle, which is 2 pi radians, they repeat. Okay. Maybe I won't. Let's do one more example of an angle. So suppose I take, now I will use degrees just for the comfort level for a minute. What if I make, so still the unit circle, I'm just getting that out of the way. Suppose you take the unit circle, but now you take an angle of 30 degrees over here. So the question is, what are sine and cosine for this angle that you make with the positive x-axis? So, well, this whole thing is 180 degrees. So it's 180 degrees minus 30 degrees. So going all the way, sorry, the whole thing. Going around to here, so this angle would be 180 degrees, but you're subtracting 30. In radians, this angle is the pi radians from going 180 degrees around. 2 pi radians is 360 degrees, pi radians is 180, minus this pi over 6. So this is 6 pi over 6 minus pi over 6. That angle is 5 pi over 6. Can we say what the sine and cosine of 5 pi over 6 are? Sure. So, what's the sine of 5 pi over 6? By the way, of course, you can do some of these on your calculator. The problem with some calculator answers, well, if you get the square root of 3 over 2 is an answer on your calculator, you're going to see the decimal. Will you recognize it as the square root of 3 over 2? I don't know. I doubt it. Also, you need to make sure if you are doing this on a calculator, you need to make certain that your calculator is set to radians instead of degrees. Okay, how do we find the sine and cosine of this? Well, you're supposed to know about 30, 60, 90 triangles from high school or from pre-cal or from something. Here's 30, 60, 90. And if the hypotenuse is 1, which it is for us, the side opposite the 30-degree angle has half that length, so it's a half. Then you could use the Pythagorean theorem to get the other side. This length has to be the square root of 3 over 2. So that this squared plus this squared is 1. Those are the lengths, but sine and cosine on the unit circle are not just lengths. They're the x and y coordinates, and so you have to be careful. Yes, this length right here is the square root of 3 over 2. And this length right here is a half. Okay, so the y-coordinate, yes, is positive a half. But the x-coordinate, oh, we're in the negative x direction. The x-coordinate is negative the square root of 3 over 2. So that means that the cosine of 5 pi over 6 is negative the square root of 3 over 2, while the sine of 5 pi over 6 is positive a half. All right. Let me sketch the graphs of sine and cosine, and then I'll give you a couple of properties, and then we need to figure out derivatives of sine and cosine. So the graphs, you can have a calculator do it. You can just kind of think about what happens to the x and y coordinates as you move around the unit circle, but let me just give these to you. Maybe you've seen these before, maybe you haven't. The graphs look almost the same, and they are, except they're shifted. Now we have another little problem. I've been saying that sine and cosine are the x and y coordinates on the unit circle, and I've been calling the angle t. But when we draw graphs, our favorite name for the independent variable is x, and our favorite name for the dependent variable is y. And so I am going to do that. I'm going to draw graphs, y equals cosine of x and y equals sine of x. Don't get confused between the x and y's that appear in the functions that I'm about to graph and the x and y coordinates on the unit circle that you use to define sine and cosine. So y equals cosine of x. Well, you're on the unit circle, so certainly the x-coordinate is always between -1 and 1. The y-coordinate, the sine, is always between -1 and 1. Your x-coordinate, so your x-coordinate, as the angle starts to increase, your x-coordinate starts dropping, and then it keeps dropping down to -1, and then it starts increasing. It starts increasing back to 0, and then it increases back to 1. The graph of cosine looks roughly like this, where this is 1, this is -1. It hits 0 at, this is pi over 2. It's -1 at pi. It's back here at 3 pi over 2. And then the graph starts repeating at 2 pi. Cosine is 2 pi periodic, so the graph just starts over, and same thing happens in that direction. The graph just repeats. What does sine do? Essentially the same thing, except shifted. So if you look at the y-coordinate on the unit circle, it starts at 0. As the angle starts getting bigger, your y-coordinate goes up to 1. Then it drops back down to 0. Then your y-coordinate goes to -1, and then it's back at 0. What sine does, it still goes between plus and -1. But it starts at 0 and it goes up to 1, down to -1. It does this kind of thing, where this is pi over 2. Yes, my scales are apparently different from that picture to this picture. Pi over 2, pi, 3 pi over 2, and 2 pi, where it starts over again. Those are the graphs of sine and cosine. Yeah, they look the same. If you shift this one over pi over 2 units, you will get that one. Pretty much every relation you see between this graph and that graph corresponds to a trigonometric identity relating sine and cosine. I don't want to go through them all, but there is the fundamental trigonometric identity. Sine and cosine are points on the unit circle, and points on the unit circle all satisfy that x squared plus y squared equals 1. So it means that sine squared plus cosine squared always equals 1. So this is the fundamental trig identity. That sine squared t plus cosine squared t equals 1. This is the identity means an equality of functions. It means this function equals this function. So what that means is for all t. This is the fundamental trig identity. I should also say that this means, this notation, this is short for writing sine of t quantity squared. You put the squared there instead of having to write the parentheses and the squared there. You can do that for any power except -1, where the -1 would indicate an inverse trig function that we'll talk about in later sections. But yeah, for every power other than -1, if you write the power there, it means this with the power there. Same thing. All right, this is the fundamental trig identity. Then there are angle addition formulas that are important. I will not derive these. Hopefully you've seen them, and if not, you can just take them as given. Angle addition formulas for all angles alpha and beta. The cosine of alpha plus beta is the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. And the sine addition formula, the sine of alpha plus beta is the sine of alpha times the cosine of beta plus the sine of beta times the cosine of alpha. All right. Okay, at this point I'm kind of finished with reviewing or summarizing most of the properties of sine and cosine that we need, that ideally you would have had in an earlier course, and defining radians. Now we want to look at information about sine and cosine that pertains to taking their derivatives. This is a calculus course, and we want to be able to take derivatives. We want to understand the instantaneous rate of change of these functions. And so we need to know things about limits involving sine and cosine. We'll get those mainly by using the pinching theorem, and I'll remind you what that says, but I need to draw another picture. So put back the unit circle. And I want to draw all right, so here's the origin. Let's see, if I want to agree with what's in the book, I need A, B, C, D there. I need A, B, C, D. All right, so this is a right triangle. This is a right triangle. And this is all the unit circle. So this is a circle of radius 1. So this is supposed to be this length is supposed to be 1. The angle here, well, it's just, since this is the unit circle and we're dealing with radians, the angle is just the length of this arc right here. So I will call that, this is t. What are you supposed to get out of this picture? Well, several things. First of all, this point, by definition, has x-coordinate cosine of t and y-coordinate sine of t. So I guess I'll get that out of my picture by writing it up here somewhere. So this point has coordinates cosine of t, sine of t. All right, so it means that this length down here, so the length of OD is the cosine of t, and this height, so the length of BD is the sine of t. Okay, what else do you get from this picture? Well, this big triangle, OCA, is similar to this small triangle, OBD, which means the ratio of this side, BD, to this side equals the ratio of this side to this side. But this side has length sine of t divided by this, which is cosine of t. So we get sine of t over cosine of t equals this length divided by this length, but this length is 1, so this is the length of AC. All right? Okay, so now what do you want out of this triangle? Well, I'd like to look at the area of this sector. So a sector, this like piece of pie that's sitting here, this curved part, this portion of a circle. What is the area of a sector? You might go, well, I don't know a formula for the area of a sector. Actually, it's pretty easy. The area of the sector, so I'll write this curved. I'll try to draw this piece of pie looking thing. The area of the sector OAB, well, it's whatever fraction of the area of a circle, that this angle is a fraction of the total angle in the circle. All right, what's the total area of a circle of radius 1? The area of a circle, pi r squared. This is a circle of radius 1. Its total area is pi. So we get some fraction, so pi times 1 squared. We get some fraction of pi. What fraction of pi do we get? Well, we get the fraction that corresponds to what fraction of the circumference t is of the entire circumference. Well, the whole circumference is 2 pi, and we've got t's worth of that. So we've got t over 2 pi is the fraction of the circumference we've got, and the corresponding area of that sector would be pi times that. The pi's cancel. It's just t over 2, which is kind of a surprisingly simple formula, but yes, the area of a sector where that on a unit circle where this arc length is t is just t over 2. Okay, great. Well, what do we see in this picture? We see that, well, certainly the area of that sector is greater than the area of this triangle OAB. Right? There's a sector OAB and there's a triangle OAB, and certainly that area of the sector is greater than the area of the triangle. So, but the area of the triangle is 1/2 the base times the height. The base has length 1. The height is sine of t. So we get 1/2 the sine of t. And finally, certainly the area of that sector, though, the sector OAB, is less than the area of the big triangle OAC. And what's the area of the triangle OAC? It's 1/2 the base times the height. The height is still, the base is 1, so you get 1/2 times 1 times the height, AC, which we already figured out was the sine of t divided by the cosine of t. So we get 1/2 the base, which is 1, times the height, which is sine of t, over cosine of t. And so what we're getting is, well, 2 or 3 inequalities, depending on how you count, which ones you want to count as serious inequalities. But we get that the smallest area here is the area of OAB, so that's 1/2 the sine of t. So we get 1/2 the sine of t is less than the area of the sector, which was t over 2, which is less than the area of the big triangle, which is 1/2 sine of t over cosine of t. And then certainly this area is greater than 0. And this is for, well, we need for our picture to be accurate. This is only good for t between 0 and pi over 2. Right? Otherwise, we're not looking at the right picture. Okay, so what do we get from this? Then what we get, if you just look at these inequalities, you certainly then can conclude, all right, this is strictly greater than 0. Well, then it's certainly greater than or equal to 0. And I'm going to multiply these inequalities by 2. 2 is positive. It leaves the inequalities in the same direction. And I'm going to weaken it because we only need it weaker. But we get this. Yes, we actually know they're strict equalities, so this is certainly true. I'd like to know the limit as t approaches 0 of sine of t. Well, we have the pinching theorem that says, oh, if sine of t is between 0 and t, and we know as t approaches 0, this certainly sits there happily being 0. As t approaches 0, this approaches 0. So since this end and this end both approach 0, this limit in the middle is trapped, and so the limit as t approaches 0 of sine of t also has to be 0. This is true, but I've cheated. I cheated because here it's not so important that t is less than pi over 2 because we're happy with t arbitrarily close to 0. But it is important that this was only correct for positive t's, and this limit means the limit as you approach from the left or the right, so through positive values of t and negative values of t. What you have to do is a separate argument for t less than 0 that's analogous, that looks just like the argument we did for t greater than 0. And you combine the limit from the right and the limit from the left. They both have to be 0 by one-sided versions of the pinching theorem. So you get that the limit as t approaches 0 of sine of t is 0. From this, it's kind of cool. You can conclude from this without extra geometric arguments that, in fact, the limit as t approaches 0 of cosine of t is 1. How do you conclude that? Use the fundamental trig identity. Sine squared plus cosine squared is 1. But that means that cosine of t is plus or minus the square root of 1 minus sine squared t. But if you look at t between minus pi over 2 and pi over 2, well, then the x-coordinates there are positive. So you have this if t is between pi over 2 and minus pi over 2. And so certainly 0 is between minus pi over 2 and pi over 2. So the limit as t approaches 0 of this is the limit as t approaches 0 of this. But we know how limits and compositions of functions work. And we conclude that, oh, since sine of t approaches 0, as t approaches 0, cosine of t approaches the square root of 1 minus 0 squared, so 1. So we get that the limit as t approaches 0 of sine of t is 0, the limit as t approaches 0 of cosine of t is 1. Well, this just says that sine and cosine are continuous at t equals 0, because the value of sine of t when you plug in t equals 0 So sine of 0 is 0. And cosine of 0 is 1. So this just says that their limits equal their actual values when t is 0, which means that they're continuous there. But we get something else from this as well. So here we had sine of t is less than or equal to t. So if you divide by t, now assuming t is still greater than 0 and less than 2 pi, so assuming this still, then if you divide both sides of this inequality by t, so we're assuming t is positive, so we have this, divide by t, you get that this is less than or equal to 1. Okay, fine. What else do we get? Well, if you look at this inequality and multiply by 2, you get that t is less than sine of t over cosine of t. You can divide by t and multiply by cosine of t, keeping in mind that cosine of t is positive in this range, so you don't change any of the inequalities, the directions of them. You will get that cosine of t is less than sine of t over t. We're happy with less than or equal to. Less than would be fine. But we get this. And we also know that this is less than or equal to 1. Oh, but as t approaches 0, we just saw that this limit approaches 0. Well, it's the pinching theorem again. As t approaches 0, this 1 just stays 1. This limit as t approaches 0 is 1. So sine of t over t has no place to go. It gets pinched in between. The limit as t approaches 0 of sine of t over t is 1. This is correct if t is in radians. This is completely wrong if t is in degrees. You get this. And again, I really only showed you this as t approaches 0 from the right through positive t values. You have to do a separate argument as you approach through negative values, but it's essentially the same, and you do conclude this. We can also use this to say what I want, that the limit as t approaches 0 of 1 minus cosine of t over t, that this is 0. Why is that true? You actually use this in a cool way. You want to know what this limit is, so you use mathematicians' stupid trick number 2. You multiply by 1 in a clever way. What's the clever way to multiply by 1 in this problem? It's to multiply the numerator and denominator by 1 plus the cosine of t. What's so clever about that? Well, what's so clever about that is you can use the difference of squares. Here's 1 minus the cosine of t times 1 plus the cosine of t. That, as you should have seen by factoring the difference of squares this way, that's the same as 1 squared minus cosine squared. So it's 1 minus cosine squared. Oh, but the fundamental trig identity says that 1 minus cosine squared is sine squared. So the numerator now becomes sine squared t, and you get divided by t times 1 plus the cosine of t. But now you split off a sine t over t factor. So this is the limit as t approaches 0 of, you write it as sine t over t times, you're left with another sine of t in the numerator, and then 1 plus the cosine of t in the denominator. And now as t approaches 0, this part approaches 1. Now as t approaches 0, this numerator approaches 0. The denominator approaches 2. 0 over 2? I'll do it in my head. 0. So you get 1 times 0. This is 0. Right. So you get these two limits. The limit as t approaches 0, the sine of t over t is 1. The limit as t approaches 0 of 1 minus cosine of t over t is 0. And those are what we need for finding the derivatives of sine and cosine combined with the angle addition formula. So let me write these again. we know that the limit, now I'll put h's in place of t because we like h in our limits for derivatives, but you don't have to do this. The limit as h approaches 0 of sine of h over h is 1. And the limit as h approaches 0 of 1 minus the cosine of h over h is 0. All right. What do we get from this? We get a theorem. The derivative of sine is cosine. And you might think, so I'll bet the derivative of cosine is sine. Yeah, that'd be close, but there's an extra minus sign that comes in. So the derivative of cosine of x is negative the sine of x. How do you show this? You have to use the definition of the derivative. But now that we have those two limits, it's going to be easier for us, or it's going to be easy for us, assuming you also know the angle addition formulas. So let me do one of these and leave the other one as an exercise or something for you to read in the book, but let's do one of them. So, for instance, the sine of x, its derivative. You have to go back to the definition that makes the derivative the instantaneous rate of change. It's the limit as h approaches 0 of, you take sine of x plus h minus the sine of x over h. Here, you use the angle addition formula. So you take the limit, you get the limit as h approaches 0 of the sine of x plus h is the sine of x times the cosine of h plus the cosine of x times the sine of h, and then minus the sine of x, all divided by h. So what do you do? Well, you see a sine h over h here. Yeah, that's good. Then if you factor a sine of x out of this term and that term, you get a cosine of h minus 1. So if we factored out a minus sine of x, we'd get a 1 minus cosine of h. So you rewrite this in a way that sets us up to use the two limits that we just discussed. I'm going to factor out a minus sine of x. From here, that would leave you with a minus the cosine of h. And then a minus sine of x from here, you'd get a plus 1. And then here, well, it's already set up for us, cosine of x, sine of h. And then it's all divided by h, so I can write that as, well, I can write that as just this part divided by h and this part divided by h. And so you get this. Maybe I'll put these here. So, what do you get? You get this as h approaches 0. But sine of h over h approaches 1. So you get 1 times cosine of x. That's cosine of x. 1 minus the cosine of h over h as h approaches 0. This part approaches 0. 0 times minus the sine of x, 0. So you get 0 plus 1 times the cosine of x. You get the cosine of x. The derivative formula for the cosine of x is equally as easy once you know the angle addition formulas and these two limits. All right, so now we know the derivatives of sine and cosine. We could combine those with any of our other rules. It's worth looking at the second derivatives for a second. I mean, we already gave you the graph, so we've already looked at where the second derivative is positive and negative graphically. But it is kind of cool what happens when you take the second derivative. So what's the second derivative of sine of x? Well, it's the derivative of the derivative. So it's the derivative of cosine of x. But the derivative of cosine is minus sine. All right, so sine of x, it's kind of reminiscent of e to the x. The derivative of e to the x is e to the x. The second derivative of sine of x is not sine of x again, it's negative sine of x. What about cosine of x? Its second derivative. Well, here's the derivative, and then the second derivative you would differentiate this. But the derivative of sine is cosine, so you get negative cosine. Oh. So the same sort of thing, the same kind of thing happens for cosine. Its second derivative is negative what you started with. Both of these, so both y equals sine of x and y equals cosine of x satisfy, well, a differential equation, namely that y double prime equals negative y, right? Sine and cosine both satisfy the property that if you take their second derivative, you end up with negative what you started with. And in fact, you can show, and it's in the book, I'm not going to do it, you can show that anything with this property, that its second derivative equals negative the function itself, has to be some constant times sine plus some constant times cosine. But let's, as an example of using these derivative formulas, let me do a couple of physical examples. And so you might think, you know, sine and cosine, I said they were fundamental periodic functions. Yes, they have period, 2 pi. But how often do you have problems with things moving in circles? Like, why would sine and cosine come up? And the fact of the matter is that usually sine and cosine come up in problems that have nothing to do with anything moving in a circle. It's just somehow that motion around a circle gives us these fundamental functions that come up so often in other situations. So here's a typical situation. Suppose you have a spring attached to a wall, and then it's attached to some block. So here's some block. This is a spring. I'm going to assume that the floor is frictionless. I'll put in friction in a few minutes, but I'm going to assume this is frictionless, which doesn't happen in the real world, but you can make it close to, you can make that a reasonable approximation. You can coat the floor with oil or something. So you have a mass, so you have this block on a spring, and if you just let the spring sit at its natural length, the center of the block would sit at some position, and we call that position 0, and it's also called the equilibrium position. And I'll label this as the x-axis, and to the right of the equilibrium position will be the positive direction, to the left will be the negative direction. What do springs do? Well, when you pull the spring, when you pull the block this way, the spring will pull back that way, so there'll be a force exerted on the block in that direction. If you push the block this way, the spring is compressed and the spring exerts force to the right. So the spring always acts to oppose the position of the mass. So if the mass is here, so in the positive, has some positive x-coordinate, the force is pushing in the negative direction. If the coordinate, the x-coordinate of the center of the block is negative, the spring pushes in the positive direction. You can actually, in the book, they discuss, or we discuss, Hooke's law, and that springs, the spring force is proportional to the displacement. But really that discussion belongs in differential equations where you actually solve for the position of the mass. That's a little harder than what I want to discuss now. It would take a long time. So I just want to give you the type of answer you get from analyzing the forces acting on the block. What do I mean by the answer? I mean, you get the position as a function of time. So we're just going to assume that we have started this block moving, that either we initially displaced it and let it go, or we left it there but we hit it with something so we started it moving, or we just started, it was already moving and we just started talking about it at some time that we called 0. So we're going to assume that we know how these things work out. we're going to assume that x equals, and if I want to use exactly the numbers that are in the book, we'll assume x equals 2 cosine of 3t. Where x is in meters. And t is in seconds. So what I'm saying is, yeah, you let this start moving, and this would be a reasonable function describing the position of the mass as a function of time. And so my question is, I have lots of questions, like, so why don't we find the position, velocity, and acceleration of the block at t equals 0 and pi over 2 seconds. And while we're at it, when does the block repeat its motion? So I'm claiming that this function is periodic, and I'd like to know how often it does it. So when does the block return to its initial position? All right, so let's look at all of these. So x is 2 cosine of 3t. You should look at this and understand some things immediately. Cosine is always between plus and minus 1. So 2 times that is always between plus or minus 2. We call this 2 the amplitude. The amplitude of the motion or the oscillation of the oscillation. And I should have said this explicitly, because this is the position function, this is going to be periodic, and what's going to happen, and maybe it's intuitively obvious if you assume there's no friction, that if you move the block over here and let it go, the block's just going to bounce back and forth, passing through the equilibrium position, going, well, to a position of -2 over here, then oscillating back to 2, and it's just going to theoretically keep going back and forth. In real life, you couldn't make this exactly frictionless, and eventually it would slow down and stop at equilibrium. But all right, so what's the velocity? I'm going to go ahead and calculate the velocity and acceleration, and then plug in t equals 0 and pi over 2. So what's the velocity? The velocity is the instantaneous rate of change of the position with respect to time. So it's the derivative of the position with respect to time. It's dx dt. So the velocity, v, is dx dt. The derivative, well, derivative 2 times something, you get 2 times the derivative of, so x is 2 cosine of 3t. We want to differentiate this, so the 2 is just a constant. You just pull that out. The derivative of cosine is minus sine. So you get minus the sine, you leave the inside stuff the way it was, but by the chain rule, you have to multiply times the derivative of 3t, so times a 3. Right. Chain rule. Derivative, here's one function done to t, another function done to that. The derivative of a composition of functions You differentiate the outside function. Derivative of cosine we just saw is minus sine. You leave the inside stuff how it was, but then you multiply times the derivative of the inside. Writing this more nicely, we get a minus 6 sine of 3t. Units, x units divided by t units, meters per second. And the accelerations, the derivative of the velocity. So the instantaneous rate of change of the velocity. So the minus 6, you just pull that out. The derivative of sine, we just saw as cosine. The 3t stays 3t, but by the chain rule, you have to multiply it again by the derivative of the 3t, so you get another 3. So you get minus 18 cosine of 3t meters per second squared, or meters per second per second. Okay, so there's the position. And they're not in a good order anymore. So this many meters. The position, the velocity, and acceleration. At t over, we want at t equals 0 and t equals pi over 2. So at t equals 0 seconds, what do you get? You get x at 0 is the cosine of 0. That's 1. So you get 2 times 1, so 2 meters. So it's 2 meters, and with a plus sign, that's 2 meters to the right of equilibrium. All right, what's the velocity at time 0? It is the sine of 0, or minus 6 times the sine of 0. But the sine of 0 is 0, so this is 0 meters per second. So yeah, right? At time 0, so what's happened at time 0 is, this is the equilibrium position. We pulled the block over to like the 2 meter position. So we pulled the block over to here. So the string would be stretched. We pulled the block over to here, and we let it go, starting with 0 velocity. The acceleration at time 0, negative 18 times the cosine of 0. Cosine of 0 is still 1. Minus 18 meters per second per second. The minus sign means it's accelerating in the negative direction, that way. Yeah, right. That's the way the force of the spring is pulling. So yeah, it's accelerating in that direction. What happens at t equals pi over 2 seconds? Well, x at pi over 2. All right, what's x at pi over 2? It's 2 times the cosine of 3 pi over 2. I'll remind you that 3 pi, I'm going to draw the unit circle. There's the unit circle. Pi over 2 radians is 90 degrees. 3 pi over 2 would take you all the way around to here. And you're looking at the x and y coordinates of this for cosine and sine of 3 pi over 2. But that point has coordinates. Its x coordinate 0, its y coordinate is minus 1. So x at pi over 2, 2 times the cosine of 3 pi over 2. But the cosine of 3 pi over 2 is 0. So this is 0 meters. The mass, the block is at the equilibrium position. What's the velocity at time pi over 2? It's minus 6 times the sine of 3 pi over 2. But the sine of 3 pi over 2 is minus 1. So you get minus 6 times minus 1. You get 6 meters per second. So the block is headed, at time pi over 2, the block is here and is headed in the positive direction. Its velocity is that way. So somewhere in between, the block turned around, right? The block, at time 0, you were here, you let it go. It presumably passed through equilibrium, made it down to minus 2, and then it started back, it passed through 0, and is headed that way at 6 meters per second. The acceleration at pi over 2 is minus 18 cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0, so this is 0 meters per second. that shouldn't come as a surprise. Right at that instant in time, the block is at the equilibrium position, and the spring is in its natural length, and it's not exerting any force right in that instant in time. So yeah, the position of the block is 0, the acceleration is 0, but the velocity, the mass is headed to the right. Okay, when does it return to its initial position? Well, it's just if you cosine repeats, every time what you're taking cosine of goes up by 2 pi. So if you think of this as starting at time 0, the next time this cosine wave repeats, the next time things start over, so is first time when you're back to where you started, is, well, it's when 3t, so 3t starts out, if you think of starting at time 0, that starts out at 0. It's when what you're taking cosine of, the entire angle, this 3t, goes around 2 pi. Cosine is 2 pi periodic. So the question is when 3t equals 2 pi. i.e., t is 2 pi over 3 seconds. So yeah, this function with the 3 there, this is still periodic, just like cosine itself is periodic, but the period changes. It's not 2 pi anymore with the 3 there. It's 2 pi over 3. It repeats more often. Right. So that's when the block will first return to its initial position after time 2 pi over 3 seconds, the period of this oscillation. Okay, that's what a mass on a spring, or that's a typical example of how a mass on a spring with no friction oscillates. I can change this a little bit. Or actually, it's a significant amount. It's not a little bit. If you assume that the floor has friction, so it's not frictionless anymore, that the floor exerts some force on the mass due to friction, and that the friction is proportional to the velocity, which is not a bad approximation of how friction frequently works. If you do that, then a typical function that you would get for the solution to the appropriate differential equation, so a reasonable function that you might get as the position of the mass, of the block as a function of time, is this. This is exactly what I just had, except I put in this e to the minus t factor. What does that do for you? Well, if you think about it, e to the minus t is always positive, and this part oscillates, but this part oscillates between plus and minus 2. But then this e to the minus t is there, so you're always between 2 to the minus t and minus 2 to the minus t. And what happens, I'm going to exaggerate what happens just so I can draw it fairly well, but if this is the position in meters, again, measured from the equilibrium position, so now I'm assuming we have friction. And it shouldn't surprise you that what happens is your oscillations get what's known as damped out. The wave, you still see this kind of waving motion for a while, but as time goes on, yeah, you see an oscillation, but the amplitude of the oscillation, how high and how low it goes, keeps decreasing, and eventually you get so close to the t-axis that you can't see the difference. In theory, you'll never just be the constant. This will never reach just where it stays a flat line along the t-axis where x is 0. But realistically, that would happen. You'd have to take in quantum effects or something more atomic once it's moving at about 1 nanometer per century. All right. Let's ask the same questions for this, just to get used to how bad the calculations can be. First of all, we don't expect this to be periodic. It won't return to its initial position. But we can still ask for the velocity, the acceleration, the position, the velocity, and the acceleration at these two times and see how much worse the calculation is. And also it's good practice using our new derivatives for sine and cosine in combination with our other rules. So we have x equals 2 e to the minus t cosine of 3t. The velocity, the derivative of the position with respect to time. How bad is this? Well, it's not so bad, but it's not so good. This is the product of two functions of t. There's e to the minus t and cosine of 3t. So you have to do the product rule first. Yes, we'll have to do some chain rule, but that'll be second. You apply the rules first to kind of the last thing that was done to the functions there. Lastly multiplied together. So you apply the product rule. You get it's the first thing times the derivative of the second. I'm not actually going to take the derivatives yet. I'm just writing the product rule. I pulled out the 2, but then it's the first thing times the derivative of the second plus the second thing, the cosine of 3t, times the derivative of the first. This. So we have to do this. Yuck. But, oh well. You get e to the minus t, and then you have to differentiate this like we did a minute ago. This requires the chain rule. So you take the derivative of the outside function, cosine, you get minus sine, you leave the inside stuff the way it was. But then by the chain rule, you have to multiply times the derivative of 3t. That gives us a 3. Plus, you get this cosine of 3t. And then this also is the chain rule. Remember, the outside function is the exponential function, raising e to powers. The inside function is minus t. The derivative of e to something, you get the e to the something back. But then by the chain rule, you have to multiply times the derivative of the exponent. And so we pick up an extra minus 1. So you get this relatively ugly thing. We can factor in e to the minus t out of this term and this term and end up with, this is all in meters per second. I'll write that at the end. But you can make this look a little nicer and also set us up to only do one product rule for the acceleration. We get that the velocity is 2 times. Factor out an e to the minus t. In fact, why don't we factor out a minus e to the minus t? There's a minus sign and an e to the minus t, and a minus sign and an e to the minus t. So I'll factor out a minus e to the minus t, and I will get 3 sine of 3t. A 3 sine of 3t and a plus the cosine of 3t. All right, meters per second. It's not going to get any nicer. That's not so good, but it's not so bad. And then the acceleration is the derivative of the velocity with respect to time. All righty, here we go. It's minus 2 times. And then, again, you have to do the product rule. There's e to the minus t times this stuff in the square brackets. So the product rule, you get the first thing, the e to the minus t, times the derivative of the second thing. First thing times the derivative of the second plus the second thing, all this stuff in the square brackets, times the derivative of the first. So now I've got different square brackets here, but this second thing, the 3 sine of 3t plus the cosine of 3t times the derivative of e to the minus t. Uh-huh. And so you get a minus 2. All right, there's the minus 2. That was the easy part. And then the first thing times the derivative of the second. All right, we get e to the minus t, and the derivative of this, you pick up, you get a 3. Then the derivative of sine is cosine, but then by the chain rule, you pick up another 3. So we end up with 9 cosine. Actually, let me separate this from what I'm about to write. We get a 9 cosine of 3t. And then the derivative of this part, you get a minus 3 times the sine of 3t. Minus, because the derivative of cosine is minus sine, and that extra 3 is from the chain rule, the derivative of 3t, you get another 3, but I wrote it on the left for aesthetic beauty. Plus, so this minus 2 is multiplied times all of this, but we get plus this 3 sine of 3t plus the cosine of 3t. And then the derivative of e to the minus t is still minus e to the minus t. All right. And so what are we getting? Let me simplify everything and write them, or simplify. Let me simplify A. So let me write everything where we can see them all at once. So we get x, 2 e to the minus t cosine of 3t. What we found for v is right, it's over there. It is, we found v. That is not a prime. It's just a smudge on the board. Oh, I'm dropping the units, but it's meters, meters per second, meters per second, per second. Here we got minus 2 e to the minus t times 3 sine of 3t plus the cosine of 3t. As you can see, this is a lot harder. As soon as you put in the friction and make the problem more realistic, things get harder. That's not terribly surprising. It is a good exercise at calculating derivatives using the product rule and the chain rule and our new formulas for the derivatives of sine and cosine. What did we just get for A? Well, a mess, but let's see. We can once again, I will factor out, I guess I'll go ahead and factor out a minus e to the minus t again. So here's an e to the minus t. I'll change the signs here because I'm pulling out a minus e to the minus t. There's a minus e. So I will get that A is 2 e to the minus t, and then times what? All right. If I write this as minus e to the minus t, then this is a minus, this is a plus, and I factored out this minus e to the minus t, and I factored out that minus e to the minus t. So I'm left with sine terms and cosine terms, and what I get is I get a 3 sine 3t plus a 3 sine of 3t, so that's 6 sine of 3t, and then a minus 9 cosine of 3t plus 1 cosine of 3t, so we get a minus 8 cosine of 3t, and a plus 6 times 3 sine of 3t plus 3 sine of 3t plus 6 times the sine of 3t. Yippee. All right. Assuming I've made no mistakes, what do you get? And t equals 0 seconds. We get at the position. So at t equals 0, e to the 0, that's 1. Cosine of 0, that's 1. We just get, it's 2 meters again. So it's 2 meters to the right of equilibrium. V at time 0. All right. At time 0, this is a 1. At time 0, this would be sine of 0. That's 0. This is a 1. So it's not motionless at time 0 this time. At time 0, this is a 1, this is a 1, and we get its velocity is minus 2 meters per second. All right? So it was not motionless at time 0 this time. It was still 2 meters to the right of equilibrium, but now it's moving to the left at 2 meters per second. All right, what about the acceleration at time 0? The acceleration at time 0, all right, this is 1, and then this is 0, but at time 0, this is 1, so we get a minus 8 times 2, so we get minus 16 meters per second per second. So it's accelerating to the left. It's already moving to the left, but it's accelerating to the left. All right. What happens at t equals pi over 2 seconds? Well, this is just an exercise in trig functions, but maybe it's a good exercise. You get x at pi over 2. All right, we get 2e to the minus pi over 2 times the cosine of 3 pi over 2. Well, the cosine of 3 pi over 2 is still 0, just like it was before. So x at 0 is 0. So it's back at the equilibrium position at time 0. What's its velocity at time pi over 2? By the way, pi over 2, don't think that pi, you should think of it as 180. Pi over 2 seconds, pi is about 3. So this is about 1.5. It's after about a second and a half have gone by. So the velocity at time pi over 2, you get a minus 2 e to the minus pi over 2. And then times what? All right, when t is pi over 2, this is cosine of 3 pi over 2, that's 0. But here's times 3 times the sine of 3 pi over 2. And the sine of 3 pi over 2 is negative 1. So we get times a negative 1. So we get a positive 6, right? Negative, negative, positive. A positive 6 e to the minus pi over 2 meters per second. E to anything is positive, so the block is moving to the right. That's a positive number. The block is moving to the right. So the block's at the equilibrium position, moving to the right at that velocity, at that speed. Finally, the acceleration at time pi over 2. All right, you get a 2 e to the minus pi over 2 times what? All right, time pi over 2. This is cosine of 3 pi over 2. That's 0, but we get a 6 times minus 1. Times 6 times minus 1. So that is a minus 12. Minus 12 e to the minus pi over 2 meters per second per second. So this might look confusing. After all, the mass is at the equilibrium position. So the spring shouldn't be exerting any force on it instantaneously. Right, but the friction force is still present. Right? And since the mass is moving, so you're at the equilibrium position where the spring is at its natural length, and so it shouldn't be exerting any force instantaneously. The mass is moving to the right, but the friction force always acts to oppose the motion. And so the friction force has to be pushing to the left, and it's pushing with enough force to produce this much acceleration to the left, which is indicated by the minus sign. All right. You should, of course, look at a bunch of the exercises at the end of the section where you'll have some more basic derivatives involving sine and cosine to try. These aren't so bad. We use the product rule and the chain rule. You need to get used to the derivatives of sine and cosine, because in the next section we're going to do the other 4 trig functions, tangent, cotangent, secant, and cosecant, and to handle those derivatives well, you have to be comfortable with the derivatives of sine and cosine.